Well, good morning, everybody, and welcome to Ellensburg, Washington, USA. You're looking live onto the campus of Central Washington University on a crystal clear morning. Crystal clear morning, bluebird skies, 19 degrees Fahrenheit. Most of the snow has been melted, but it's frigid, or at least, it's a little nippy in the air, but we can handle it, especially because of the clear skies. No fog, no dismal, stale air, lots of freshness and lots of sun here in Central Washington in mid-January of 2025. Thank you for joining us today. I thought my mouth was warmed up. Maybe it's not. The local time is 7:47 a.m. Pacific time. Today's date is Saturday morning, January 18th of 2025. This is episode O, and we will begin the episode officially in about 12 minutes from now. But this is live. We have more than 300 live viewers standing by. I need to scroll back to make sure we're loud and clear. We are, thank you. Where are you viewing from this morning? Can I say hi to a number of you, please? And then a couple of reveals, I guess. Too dramatic. A couple of small things, and then we will begin. Jocelyn is from Quebec, Canada. Good morning. Cincinnati, Ohio. Hurricane, Utah. Estacada, Oregon. Huntsville, Ontario, Canada. Another Canada. We got Red Deer, Alberta. Oh, the Canucks are in the house. Hey-oh. Gifford, Washington. Springfield, Oregon. Spokane, Washington. Let's go. Zurich, Switzerland. Sophie, what up, homie? Elmer City, Washington. Deep in the Chuckanut of Washington. Newland, North Carolina. Ottawa, Canada. Menominee, Michigan. Portland, Oregon. New Plymouth, Idaho. Puyallup, Washington. Hello, Gene. It's been a while since I've seen your name. Jim from Chico, California. John from Spokane Valley, Washington, USA. John's in Media, Pennsylvania. Red Lester says, London calling. Grandpa Carl, the Granger Clay Pits. Hello, Grandpa Carl. Hope you're doing well. Alan is in Portland, Oregon. I'm down to live. Port Deposit, Maryland. Port Deposit. Interesting name. Kind of bland, I must say. Gail says it's 18 degrees Fahrenheit up there in Tonasket. Yeah, Gail. About the same here. Dan's in Davis, California. Colorado Springs, Colorado. Gary Paul, backcountry Gary Paul, is frozen along the Darrington Devil's Mountain Fault. Nice to see you back here live, Gary. Thank you for joining us today. Sharon is in Malaga. Quartzsite, Arizona. Kirk is in Philomath, Oregon. Fairfield, California. Marion, Virginia. West Dallas, Wisconsin. Davis, California. Penticton. Hello, Janet, with your Canadian flag. Paul's in Glasgow, Scotland. Good afternoon, or maybe even good evening. Sun's just coming up here now. Göteborg, Sweden. That's Valentina and Kirk. Rick is Salem, Oregon, 33 degrees. John's the only Youper we've got here, Upper Peninsula. Vincent Sampson is in Montreal, Canada. Hello, Vincent. Liz and I really enjoyed your city last July. Cincinnati, Ohio. Josephine is watching with her 2-year-old. Hello, 2-year-old person. Hello, miniature 2-year-old person. Glenn is in Yelm, Washington. Winter Garden, California. And so on. So last episode I shared this with you and said that I received this gift courtesy of Ryan Hollister's website. But Ryan was careful to point out, eruption. Ryan was careful to point out that he was the middleman. He wasn't the actual person who bought the gift. So I rechecked the paperwork that came with the gift, and the gifter was revealed. The gifter's identification, Jerome Lessman, Vancouver Island University, Nanaimo, British Columbia. So I have thanked Jerome by text. I'm thanking Jerome again if he happens to be here right now. And Jerome has been worried about Liz. He hasn't been watching these programs. He's been busy doing other things, so he still was very concerned. So he said, this is for tears of joy instead of tears of sorrow. Kimmy A., former neighbor across the alley, is checking in from Fidalgo Island, Washington. We miss you, Kimmy A. Was there something else? Forgotten who sent this, but thank you. I have unwrapped her. And I doubt we will get back to the green M&Ms this series, but one of the 3 downtown lectures will be featuring green M&Ms, I'm pretty sure. So we'll use this then. We'll have a little figurine with an auditorium full of 600 people. Very good. I'm feeling too relaxed this morning. I don't know why. We're still in pregame, right? Let me make a quick announcement, which I made last week, but I want to double check because we are about to crank up in addition to these live programs from my office, you know the schedule, the next five of the next 6 Saturdays. Whoa, come on. Take 2. Hey, everybody, I want to remind you that there's a Take 3. Hang on. I need to wake myself up. Bijou the cat is my buddy in the early morning hours. By the time Liz is up and going, he's mostly her buddy. But before Liz wakes up, this is my buddy. So you got to help me. Get my head right. I'm too relaxed. Come on. Help me. Bijou. Thank you, Michael from Janesville, Wisconsin, for I wonder if this will be the little, when you hover your mouse over a title slide, there's usually a little 3 seconds of action from the episode. I've noticed it's usually when there's something held up closely to the camera. So maybe Bijou will make that little... Okay, just go to it since you're fumbling like crazy. Fridays at noon. The live streams, Fridays at noon, with the entire geology department, start this coming Friday. Tim Melbourne talking about earthquake and tsunami early warning. The following Friday at noon, Chris Mattinson, professor here, metamorphic connection, dealing with critical minerals and continental growth. The next Friday, Sean Scott, former CWU undergraduate student, who now works at the Tri-Cities. Ann Egger, science education professor here, and Paul Winberry, who has been doing plenty of work in Antarctica. So I'm letting you know that if you want to add those dates to your calendar, what do you want them again? 24th, 31st, 7th. We take a week off for Valentine's Day because we are lovers here. February 21st, February 28th. Those are the featured Friday at noon talks this winter. And in the spring, we have 2 of the Spirit Lake Pluton people coming to campus. Details to come. Okay, I'm going to give you a shot out the window. I'm going to do some hot mic. I'm going to try to lock my brain in the best I can, and away we go. Thank you so much for joining us. Now we have approaching 600 live viewers. I don't know if we'll get to 1,000 live viewers like we did right after the new year, but it doesn't matter. We have a lot of people joining live. And again, I always want to make sure that you know that I appreciate you being here live. God, I thought this was going to be a good show, but I cannot say anything officially so far. Maybe my walk will help me. I will slap myself for the entire walk. And I will be semi-conscious when we begin at the top of the hour. Thank you. Wow. Hot mic. You got a beautiful day ahead. You're going to go over and hike with Liz. You're going to get out in the sun. But you've got work to do between now and then. Don't focus on that. Don't focus on Bernadette in Bangkok, Thailand. Focus on the task at hand. You like this episode. So don't just mail it in. You've got to lock in. Let's go. You're doing geochemistry today. Figure it out. Let's go. Come on, big fella. You can do it, says Mark in the United Kingdom. Thank you, Mark. That's what I needed. Hot mic. Come on, let's go. Good morning, everybody, and welcome to the headquarters of Cascade's A to Z. That's right. These are a series of live programs here on YouTube exclusively. You can't find these programs anywhere else. And they're live. And the first thing I think I want to say this morning is that everything you see here is unrehearsed. Everything you see here is stuff that I've learned in the last day or last 2 days. And you're like, I don't think I believe that. There's a lot here. All this stuff that you're presenting, this must be from a class that you've taught for a decade to kind of work out the kinks. It may not be obvious to you that I push myself to learn new things, and the new stuff comes in a day ago, a half a day ago, this morning by email, and so on. And I'm just saying that to simply say that this is a community of people. We're all learning together, and more, I'm learning from you. And whether you are a professor in geology like Jeff Tepper or Jamie McDonald, who will be featured today, or whether you are an amateur enthusiast who is sending photos from your library, or you're even going out and taking photos because you've been inspired by something we've done or are about to do, we're all bringing our enthusiasm, and I'm bringing my enthusiasm as well. But it is truly a community, and I feel like I want to point that out on occasion. This particular alphabet has developed into the visual sense where we're getting all these different kinds of photos and video clips today. So today's episode, by design, will be a variety platter. I mean, part of what we're going to do today is geochemistry. My attempt to translate what I learned yesterday from Jeff Tepper, which is on the recorded Zoom video library. But if it's nothing but geochemistry, I don't know if I'm going to have that much fun. And I'm not sure you're going to have that much fun either, unless you're really into that stuff. So you'll notice today I'll keep switching things up. We'll take a road trip for a while. We'll do some photos for a while. We'll do some video clips for a while. We'll toss in some geochem. We'll do some classroom stuff, paper stuff. And I think that's what I'm trying to do lately, and maybe what I will try to do the rest of the letters in the alphabet. He goes to Docky, the document camera, to say that I hereby declare that we are done with blue. Today is our last blue episode, and I just looked it up. We've been in blue for a month. We've been in the 40s, blue time, for a solid month. And we found a lot of stories in blue, but it's time to move on. I mentioned this last time. So I promise that the next 2 episodes, in other words, next when I say next weekend, you know I mean Thursday and Saturday. Next weekend we're going to be green, and green is the 30s, rocks between 39 and 30 million years ago. And then unless we are just shocked at what we find and need a 3rd or even 4th green episode, I really want to get to red, because that's where the Spirit Lake Pluton Project and other major plutons reside. So if you want to just continue to be a part of the community and feel like you want to contribute somehow, let me say it right now before I forget. Beyond the Ohanapikosh Formation and the Chilliwack Pluton and the Index Pluton and the Squire Creek Pluton, and I think maybe the Wenatchee Formation, beyond those 4 things or 5 things that I just said, I don't know what else is worth looking at for green time. So as I start to put together the shows for next weekend, the next 2 episodes, if you have a suggestion about something from the 30s that is not those things I just said, and you feel like emailing me, just email me with the subject green, or the subject line is green 30s. And it'll just be an idea or 2 that I might be able to fold into what we do next week. But we'll just keep that communication going, that community going. But that's the plan for next weekend. 2 green shows from the 30s. And I don't know, I think I'm ready to jump right into the content today. You're like, yeah, wow, what a change. Usually you BS for 10 minutes. No, I rarely BS. I don't think I'm getting a lot of those comments, by the way, by email and everything else. Get to the point. You're always like BSing. I don't know. I think you're missing what I'm trying to do. I'm trying to talk to everybody, the hardcore folks, and I don't need to give you an explanation, do I? So if we go to the website and we see that here we are right now happening with episode O, all of these are cataloged for you and ready to go on the website. And then if I go back to home and I click on Nick on the Rocks, these new episodes continue to come out. And we only have one more new one to go, and that's debuting next week. And Backcountry Gary Paul is with us, and Gary has his fingerprints over almost every one from the last episode, from the last season of episodes. But we have a break-off belt magma Pluton in the North Cascades, the Golden Horn Batholith, featured for the last new Nick on the Rocks episode. And we're about to start planning for this coming summer and making new episodes. I guess I'm still BSing. All right, so that's a bunch of stuff at the website that you may or may not be aware of. Although why wouldn't you be aware of it? I keep pointing it out every time we get together. If we go to the Cascade Video Library, there's a brand new conversation that I had with an old friend of ours by now, Jeff Tepper, and that conversation I thought was particularly good, and I'm going to use a fair amount of it today. Not only a few clips from that conversation with Jeff, but I'm also going to try to teach it based on how I think I understand it at the moment. If we go to the list of papers, there's a number of Jeff Tepper's students and their posters from typically Geological Society of America meetings or AGU meetings. And we'll be going to a couple of these elements within these posters. Jamie McDonald has 3 things for us. Joe Dragovich and team have a Sultan geologic map and text. And so there's plenty of backup. There's plenty of rich detail for you. But I think you see I hope you can see what my role is. My role is to not only synthesize and get some narratives established and carry the narratives through. I think my job also is to give you a reason to care about the details. That's another way to say it. I only care about the details until I can find some interesting hooks, and maybe ultimately that's what I'm trying to do with these programs. Create some hooks, some interesting narratives, and then, and only then maybe, you're really interested in digging down to the very, very minute details. Okay, let's start then. Follow the slides, see where we go. We start with a leftover thought from the last time we were together, which was just 48 hours ago. You remember Sky Cooley, also from the last alphabet, last winter with the calcretes and the Ice Age floods and so on. Sky's been watching, and Sky said, I got this yesterday from Sky. Using a Sharpie and a thumbtack, I rotated a map and dragged the pen sideways at different rates to produce this figure. Interesting to see how varying the rate of clockwise rotation or eastward migration of the mantle plume, in other words, westward plate motion, would produce a different track to Yellowstone. So Sky has this innate sense to create figures that are simple and yet meaningful, and I don't even really know I've only looked at this for a few seconds, really, to be honest. I liked it well enough that I wanted to include it here. We were talking about clockwise rotation last time, but I'll let you freeze the frame and really soak in what Sky is playing with here and maybe seeing a little bit more of what he's talking about than I am. But that's a little add-on from the last show. Thank you, Sky. Today is a continuation of thinking of the early days, light blue, of the Cascade Volcanic Arc, 46 to 40 million years ago, and we're going to visit almost every one of these units. And you're like, didn't we do that last time? No, we didn't. We avoided the magmas last time. We avoided igneous rocks last time. We were talking about sedimentary basins, we were talking about clockwise rotation, we were talking about a lot of different things. But we really didn't get to the details of the igneous geochemistry and the igneous petrology and that sort of thing. We lean heavily, for the first time really, into arc magmas. A volcanic arc, we've started that 46 million years ago, the Cascade Volcanic Arc, and that's what I'm about to try to do with a bunch of papers, is try to comprehend for myself what Tepper was talking about yesterday. But before I go there, let me go back for just a second and say, yeah, we don't have any mountains in central Washington where we now have the Cascades during SWAC time back in the 50s. And we were talking about the lazy rivers, and we were talking about the swamp and the palm fronds and everything else, right? Hot, humid time, 56 million years ago, before Silesia arrived. And then just kind of reviewing, just to set up today's discussion, also in orange time, we start building Silesia quickly. We start bringing it in. We accrete it, starting 53 million years ago down in Oregon, 51 million years ago up here in Washington. And we develop a temporary highland. You can almost think of it maybe as like the first uplift that we have recorded in what is now today the Cascades. But by 49 million years ago, we have a massive break in the downgoing Farallon plate, and we have a break-off belt. I'm not going to go through those diagrams again. We know that, but it's been a couple episodes since we've talked about the break-off belt. It's going to come back again today. Today, we actually have the leading edge of the Farallon plate using Jeff Tepper's narration, and we have Adikites forming at the leading edge of this sinking Farallon plate as we start the early days of the Cascade Volcanic Arc. But I think I want to this is a narrative we've been working on for a while. Instead of this is such a pleasing diagram from Ken Clark, and of course it's a portrayal of beautiful towering stratocones like we have today in the Cascades. In the early days of the Cascades, did we really have this? Did we even have stratovolcanoes? We'll visit some places today that are not stratovolcanoes or evidence of stratovolcanoes. We had an arc. The early days of the Cascade Volcanic Arc, we have arc magmas. But one of the messages of today is that I think we can be willing to accept all sorts of volcanic activity, not just this picture. So as much as I love this picture, I'm going to continue to wonder as we go through the rest of the letters, when are we going to get to an arc that looks like this? Is it not until recently? Is it not until the last million years or last 3 million years? Or younger than that? And so I'm wondering if the early days, which is the subject today, 46 to 40 million years ago, light blue, I'm wondering if we have mostly this. This was a diagram portraying the SWAC time, but I'm wondering, after we accrete Silesia, do we bevel most of that Silesia backstop off? And that's what I was trying to get to with Erin Donaghy last time. Does she have sediments that are continuous from eastern to western Washington, and do we basically bevel things back off to a flat time? And you're like, what are you doing? This is a weird angle. Why do you keep coming back to this? I'll tell you why. At least I'll tell you my thinking. Starting next time, we're going to be in the Ohanapikosh Formation, and most of that action in green time, at least exposed in Mount Rainier National Park area, is underwater. Green. I'm looking ahead to next weekend, but I'm wondering if there's other ways that, besides the Ohanapikosh and those deposits, I'm wondering if there's other ways that we can think about and maybe bolster the idea that we were back down to nothing once we get to the 30s. And is it like this, and there is no major mountain range in the Cascades all through the 30s? I'll just leave it hanging, but that's, I keep talking about uplift, but that's one of the reasons. I've always had in the back of my mind the Ohanapikosh is submarine, mostly. Okay. Back to our topic, though. Regardless of what the scene is like and how mountainous it is, I guess we don't care the rest of today. We're just looking at each of these places, and we're going to take a road trip, and we're going to basically go in this order. But before we start our road trip, starting at Drunken Charlie and going all the way to Gobel, before we start that road trip and go from the Mount Persis neighborhood down to the Gobel, down by Portland, okay, here we go. I'm going to try. I don't know how long it's going to take me. I'm going to try to keep it fast-paced. I want to do all this with old-fashioned papers. I want to talk about BADR. I want to talk about hornblende minerals and mafic enclaves. I want to talk about tantalum and niobium depletion valleys on spidergrams. I want to talk about something new from yesterday's conversation with Jeff Tepper, an arc within an arc. That's my phrase, but I'll let you know what I mean with that. And then a narrative involving barium-niobium ratios. Good Lord, am I really going to do this? I'm going to try. And I can be fearless because I know this community and I know how warm and wonderful and inviting and supportive you are. I couldn't do this in another setting. It'd be embarrassing. But what we have established here over the last few winters allows me to just go for things. That's what I'm trying to say. And it's not like I'm that cocky. It's just that I know who you are, and I know this series and these past alphabets have worked for you. And so that just gives me the confidence and the freedom to just try things. So thank you. That's ultimately what I'm trying to say. It's a new way to say thank you for being part of this community. Let's try it. Okay, so it's been a while since we've looked at an igneous rock classification chart. And I'm basically asking, how today do we know that the magmas are volcanic arc? How do we know that they are arc magmas? Because all those other blue, remember all those previous blue episodes, we had magmas, we had lavas, we had plutons, but they weren't arc. Rollback magmas, breakoff belt magmas, near trench magmas, indicating a ridge subduction and a migrating triple junction. None of those were the arc. We're finally to the arc, but how do we know we're finally to the arc? What in the rocks themselves, macroscopically or microscopically, confirms to Jeff Tepper and Jamie McDonald and other people who know their stuff, what tells us that we know that it's an arc? One way is to look for the BADR. If you have all four of these lavas, of these different chemistries, of varying silica contents, then that's the hallmark of a subduction zone. Full BADR is the story. Like, yeah, we're leaving the Tepper trilogy and we're about to go to green, but we're still in the initiation of the Cascade Volcanic Arc. And yeah, we are to this paper that we've highlighted a number of times, but now I'm getting to the point that BADR is a hallmark of Cascade Volcanic Arc, and BADR is having all of these lavas showing up in the mountain range. It's a mature arc, mature versus immature. All of those chemistries are possible if you have an ongoing oceanic versus continental convergent plate boundary, BADR. Compared to what? Well, the breakoff belts didn't have any A and a D. The rollback magmas didn't have any B. The near trench magmas were rich in aluminum, but they didn't have this spectrum as well. So we're finally to the rocks in the Cascades of the early days that have this spectrum of BADR, as the name implies, or as the BADR shows up on the chalkboard. Okay? So that's this. You're like, tell me more. I don't think I know more, but I'm going to keep going with how do we know we're finally to looking at igneous rocks that are from an arc, from a subducting oceanic plate. Keep going. Hornblends and mafic enclaves. We're going to see some video clips from the field with Jeff Tepper, but let me just do it verbally very quickly. The mineral hornblende has a lot of water in it. And as Jeff will explain in the field videos, if there's a bunch of water present and it gets incorporated or locked into the hornblende minerals, that's not a smoking gun for a subduction zone in an arc magma, but it's one indicator. If you have a hornblende, that's one indicator that you've got a subduction zone, an arc magma. Same for mafic enclaves. Details coming about what mafic enclaves really are, but Jeff again says it's not a smoking gun. If you got mafic enclaves, it's not an absolute that it's a subduction zone arc magma, but it's a strong hint that you're talking about a subducting plate. So, what do hornblends look like? In a plutonic igneous rock, a hornblende looks like this. These are black minerals. Did I do it under Docky? So these are black minerals that are rectangular, and sometimes even black minerals that are long and thin. And as I rotate this rock, you can see that it's sparkly, and better than that, it sparkles like a mirror. Like as I rotate this rock in front of you, can you see that these are like mirrors? They reflect light all at the same time, and then I rotate it some more, and the sparkle is gone. These are cleavage planes on hornblendes, amphiboles in other words. 2 cleavage planes at 60 degrees and 120. That's in a plutonic igneous rock. But here's what hornblendes look like in a volcanic igneous rock. Same thing, we're looking at the black minerals. We're talking about hornblende now, which is a hydrous mineral. And Jeff helps us see that if we have a ton of hornblendes in our rock, that's a strong vote for it being a subduction zone arc magma. Same idea. You can see the long and thin. You can see the cleavage planes. You can see that there's the mirror reflection as I rotate these hornblende crystals around. I got one more for you. Here's yet another volcanic rock, or a lava flow in other words, and a few of these black guys. Here's a good one here, similar to what we'll see in the Tamanous episode. They're black, they're jet black, they have 2 cleavage planes, they're rectangular, in some cases even long and thin, like pine needles. Hornblende, a key mineral that I think we're going to keep seeing all through the rest of the arc. Not sure of that, but I guess that's one narrative we can keep an eye on. When we get to the Ohanapakash, are we going to find hornblendes? When we get to the Tatoosh Pluton in the 20s, are we going to see a bunch of hornblende? When we get to the Goat Rocks lavas, are we going to see a bunch of hornblende? I assume so, but we're establishing some narratives today that we will try to keep through the rest of the alphabet. Now that we've started the arc, how much variability will we have with hornblendes as this subduction factory continues over the course of 46 million years? Mafic enclaves, also coming in today's suite of videos. Oh boy. Mafic enclaves are black, mafic in other words, black chunks that are inside of a typically light-colored pluton. So you might have a basalt chunk inside of a granite, mafic inside of a felsic. And as you'll see in the episode from Granite Falls, if you haven't seen the video yet, Jeff's going to help us see that those are not xenoliths, which are actually chunks of black rock that fell into the magma soup. Instead, they are injections of dark mafic liquid into the pluton before it was a solid pluton. So it's like squirts of Hershey's chocolate into oatmeal, and there's exchange of the minerals and the elements, change of the elements between the syrup and the oatmeal. And some of the syrup elements go into the oatmeal, and some of the oatmeal elements go into the syrup. And that mafic enclave signature also is a helpful part of determining that we probably have an arc magma on our hand. Jeff, how am I doing so far? I got my teacher in the live chat saying, wrong, screwed it up. That's okay. I got confidence. I'll just keep going. Haven't gotten to the spidergrams, but that's next. So if you saw the Zoom chat with Jeff Tepper yesterday, it's a 30-minute discussion. I'm going to grab just a few highlights from my ear that I want to share with you. And no more stalling, I got to do it. How are we sure we have an arc magma? By looking at a spidergram. Oh boy, oh boy. So this is not the first time we've looked at a spidergram. And this is just a generic spidergram from a Jeff Tepper student poster. And what do we have here? We have different elements along the bottom. Barium is going to be important today. tantalum, and niobium. Those are the three that I want to look at. And this is not me now. I'm just repeating what I think I learned from Jeff. So a typical arc magma, I'm using light blue, right? So I'm talking about the early days of the volcanic arc. Do we finally have arc magmas? Yes. Do today's magmas, which are arc magmas, 46 to 40, are they going to look generally like this on a spidergram? The answer is yes. This is an arc signature. And what is that arc signature? There's a peak, or there's a lot of rubidium and barium on the spidergram compared to the amount of tantalum and niobium. This is a depletion, a valley of these two guys here. So there's a spike and there's a valley. There's a mountain and there's a valley. And that mountain next to a valley is telling us an arc magma is present. If we did not have that, can I find dark blue? What if we had a break-off belt and not arc? And break-off was 51 to 48, if you remember, like the Teanaway bimodal. Typically on a spidergram, those break-off magmas are going to be more like this, where we're much closer to the signature of a mid-ocean ridge basalt. And the point is, break-off belts do not have a depletion or a valley of tantalum and niobium. It's kind of a flat-looking line. So we're looking for this depletion to say that we have an arc. I'm ahead of myself, but before I forget, I'm also going to something called an arc. Oh, am I going there right now? I'm kind of going there right now. So the next step, am I forgetting something? Check my notes quick, hang on. No, I'm right on. You want to see my notes? Here's the notes I did for myself this morning. Do that in hornblende mafic enclaves, then talk about tantalum, niobium depletion values. We just did this. Now make a break and say that now that we know we have an arc, here's an angle that Jeff came up with while walking to the gym yesterday morning in Tacoma, Washington. An arc within an arc. So now that we've started the early days of the Cascade Volcanic Arc, and we have 46 million years of arc magmas being cranked out in the subduction factory, is there a narrative we can keep an eye on where something might be changing over the 46 million years? Jeff says yes. And so let's establish the signature in this episode, and we'll just keep an eye on it. But we don't have to keep an eye on it. He's telling us the change coming right now. So arc within an arc, that's my phrase. I just heard that idea, and I said, oh, this is like a story arc within the 46 million year old Cascade Volcanic Arc history. Clever, maybe even annoying. Let's move on from that phrase. So I go back to the slides, and we're now to barium-niobium ratios. So here's where I really earned my salary this morning. I will try. How can looking at the ratio between how much barium in your magma versus how much niobium in your magma, how can that ratio of barium to niobium tell us about an evolving, changing chemistry during the 46 million years that we're cranking out magmas? Well, we're back to this again. So we're talking about the barium and the niobium. Now, so far we know the niobium is typically, we're looking at it to decide if it's arc or break off. Lots of niobium break off, not much niobium arc. But now Jeff says, okay, we know there's an arc signature, and we know that there's a peak for barium and a valley for niobium. But now Jeff says, let's look at the difference between the mountaintop and the valley bottom. And Jeff is saying, with a plot just coming in a second, that over the course of the 46 million years of arc magmatism, our mountain's going to get higher compared to our valley bottom. In other words, we're going to keep enriching the Cascade Volcanic Arc with barium, and the niobium is not going to change much. So we're going to have a bigger and bigger number with a ratio of barium over niobium. That kind of work for you? Let's try it again, looking at a table, and then we'll try it again, listening to Jeff Tepper, and then we'll try it again with me trying to repeat to Jeff Tepper what I thought I heard. And you're like, I already have it. What are you doing? Why are you doing this 4 times? Because I'm not as smart as you are. It takes me a few times. It takes me a few trips around the sun to get some of these concepts, especially this kind of stuff. That's why I'm doing it. So we're ultimately trying to decide, now that we know we have arc magmas, instead of break-off magmas, right? We're done with this. This is the old days. This is dark blue. I should have made that dark blue. These are the days now. These are the days. And we're injecting fluids into the wedge, the mantle wedge, and the mantle wedge is helping us make some magmas in a subduction zone. We're sending thing up. There's BADR, but before we only had B and R, bimodal. Okay, well, this table from one of the student posters is the data that Jeff is helping us see. So, light blue. I think rattlesnake is part of the Tukwila, I think. Northcraft, we know that's early days. These are all 46 to 40. We'll even include this here, right? So this is all light blue. And Jeff on this table with his student is saying, here's our barium to niobium ratio. Barium to niobium ratio. Barium to niobium ratio. If the ratio has a higher number, that means the mountain's going to be higher. If the number's lower, that means the difference between the mountain top and the valley bottom is not as much. So the trend from 46 million years ago until today, light blue here, green here, red into the 20s, yellow-brown. You know the color scheme. Purple. You know the color scheme. So as we go in the 40s, the 30s, the 20s, the teens, and the aughts, Jeff and his students are saying our barium to niobium ratio is under 20 in blue at the beginning of the subduction zone. Then we jump up to the 30s for our ratio when we get to the 30s, the 20s, and even into the teens, I guess. And then it's approaching 60 when we get real young. And you're like, okay, but I don't know what that means. Why is that important? I will try, and then Jeff's going to tell us, and then I'll try to repeat what Jeff said. Jeff is saying that to explain this rising mountain on this spidergram of barium, to explain why the mountain gets higher, why the peak gets higher and higher compared to the niobium valley, is to understand that when in the days of starting the volcanic arc, there's no barium in the wedge. Jeff says the main way to get barium into this wedge is to have barium, which is soluble, to come with the water from a subducting plate. So before the subduction factory started, Jeff says, I don't think there's much barium down here. Therefore, the magmas aren't going to have that much barium compared to niobium, which is not being injected into the wedge. But Jeff Tepper says, if we have 46 million years of ongoing subduction, that means we have 46 million years of constant enrichment of the mantle wedge with the element barium, and therefore we're going to continue to increase our barium levels with these spidergrams as we get younger and younger in the volcanic arc. Finally, Jeff says, I think the fact that this is an immature wedge to start with, where we don't have a lot of barium to start with, is telling us that there was a break-off. And that the early days, before 46 million years ago, we didn't have much barium in those magmas because we didn't have subduction at this location. Even though during the whole time the crust was thick and the crust had BADR, there's BADR, that's a mature scene, but that mature BADR is inherited subduction from long before the accretion of Siletzia. And you're like, I'm lost. If you're lost, it's okay. That was our first pass through the content. Let's go to Jeff Tepper himself and hear some of that again.
This table is that the earliest arc rocks don't have much of a slab signature. And if you look at, so they're under 20, and if you look at the most recent stuff, it's almost 60. So there's been this increase over time, and we don't have great resolution here. We sort of have three snapshots. We have oldest, which is under 20.
Yeah.
We have Oligocene and Miocene things that are around 30.
Okay.
And then we have the youngest stuff, it's around 60. So we can at least say in a general sense, there's been an increase in this ratio over time.
Okay, let me hold you up because I'm starting to lose it slightly. So I love this. This is an arc, a story arc within the volcanic arc. We are dramatically increasing these numbers as we get younger. And this is going to play out over the rest of January and into February if we keep our eye on this. But you're saying these increases is because of something changing here in the wedge?
Right. So that right where you have your pointer, those blue arrows coming out of the slab, those are delivering these elements, delivering elements like barium into the wedge. And so but they're not delivering any niobium because niobium is not soluble in a fluid. So over time, the wedge is being progressively enriched in barium. Right. And so when you melt the wedge then to make an arc magma, over time, we expect to see that ratio go up.
Yes. So there's just the more time, the more, I'm oversimplifying now, the more time we have, the more barium goes into the wedge. And so our magmas are going to be picking up more and more barium by the time they get to the surface and erupt.
Right. And they will not be picking up barium, so that ratio, niobium, so that ratio is increasing.
Right. Okay. I like that.
Okay. So this is the enigma that I had a epiphany about this morning, which is that if we look at the rocks that are erupting, they're this mature BADR sequence. They look like it's a mature arc. But this fingerprint says, no, it's not a mature arc. The mantle part of the story says we still don't have much of an arc signature. So my hypothesis, and you're the
Love it.
first person to hear it. Nobody at the gym was interested. Um,
This is a two hour old hypothesis. Love it.
is that when we had, so if Silesia accretes, the slab breaks off, it begins to create a slab window, and into that place that is underneath the modern Cascades, here comes upwelling asthenosphere. That material is never been subjected to subduction, so it doesn't have any barium enrichment. And so we just begin enriching the Cascadia mantle after subduction is restarted at about 46. But the crust was already thick from earlier subduction. So that part of the story where it's controlling whether you get a lot of rhyolite, that's already in place. But so we're seeing I think another indicator that there's been a transition in the mantle that's underneath there. We brought in some new asthenosphere because we broke off the old slab and let it come welling up. And now we're going to start contaminating it with slab fluids and making arc magmas out of it, but we're starting from scratch.
Okay, a few things to say. Jeff is so patient, and he's also putting himself out there. Like I'm talking about me being ballsy and just kind of going for it. He's doing the same thing. That was a new idea yesterday morning, and he's sharing it with me, and I'm sharing it with you. So that's the context for some of this thinking. It's a workshop. I hope you can feel the vibe of that. Some of you in the live chat, I don't think are understanding what's going on. So I'll just leave that alone. Most of you do. Next thing to say, this is not geochem the rest of today. Remember, at the top I said I purposely want to keep this moving by doing different things. But we're in the weeds right now, and I felt like it was important to have some detail as long as some of these pretty pictures of these places. I don't want this just to be a travelogue. I want this to have some meat and potatoes, and especially if we can set up some things at this level that we will keep an eye on as we get younger and younger in the history of the volcanic arc. Now, one more geochem clip where I'm repeating back yet again. And again, I'm seeing some of you like, didn't we already hear this? Are we just repeating this? I'm telling you again. We have, first of all, I'm yelling at you. It's early in the morning. I'm sorry for that. I'm just excited. I hope you can hear the excitement and not anger or something. But now I am slightly edgy because people are like, move on. I already get it. We're all trying to learn this stuff, and it's not easy. And if you think it's easy, then I guess you're beyond the scope of most of us. Congratulations. But I think the repetition is necessary and helpful. So let's do it again in a different way. We kind of had a mature rock suite from the get-go 46 million years ago, but an immature wedge.
Yes.
And we start from scratch with barium.
Barium niobium ratio is low because we have not yet built up a reservoir of slab signature elements in the wedge.
Okay, very good. Another thing I might do tomorrow before we get into that is say, remember these spidergrams. Remember some of the main rules that Jeff Tepper taught us a month ago. And one of the rules was looking at this tantalum niobium. If it's low, it's arc. If it's higher, it's breakoff.
Right. If there's no valley there.
If there's no depletion valley.
If there's no depletion, then it looks.
Okay. We've got the main points, I hope. One last look. I want to keep coming back to this as we go further along in the alphabet. I want to keep coming back to these because I think at this point at least I understand a couple basic things about how to use them. And we will get further and further away from the old story of the breakoff, but at least right now, since we're transitioning from this to this, from dark blue to light blue and then ultimately to green, I wonder if we will need to keep coming back to portions of the volcanic history of the arc that will occasionally have some sort of break or some sort of slab missing. We'll keep an eye out for that as well. But we transition to a road trip. Ready? Road trip. All right. As promised, we're going to take Jeff Tepper's slide here and use it as a road map to get us take a little tour of these units. We did a little bit of this last time, but we weren't looking at magmas necessarily. Now we're looking at magmas. And Jeff has these organized by date, and he's just picking one date. There's a range of ages that we now have for these units, but so it's not like we're going north to south necessarily. We're just going in order of 46 to 40, essentially. So let's visit a couple of these places. Drunken Charlie, what in the world? That's up in the neighborhood of Mount Persis. Jeff, a viewer from Duvall, Washington. Hi, Nick. Back in 2020, when I just started learning about the geology by watching your programs, you briefly mentioned a lake near my home. Inspired by you, I coaxed my wife into walking out to this tiny lake tucked away in the logging lands to look at some rocks. On the unassuming shore of Drunken Charlie, I told her, this lake and these rocks are important, but I don't know why. And she did her best to seem interested. And now your recent programs have me appreciating this lake more than ever. So, Jeff in Duvall, thank you. A couple of photos, more photos from 2022, rocks from road cut just to the east. I wasn't sure if I was back in Glacial Till or not. And here's a really nice photograph of a volcanic rock from the Drunken Charlie complex, which is one of the oldest magmas of the earliest days of the Cascades. Jeff Tepper, I wonder if that's an adakite. If we're right at the dawn of the Cascade Volcanic Arc, why wouldn't that be part of the leading edge of the Farallon coming down? Just wondering out loud. Good, let's keep going. Thank you, Jeff in Duvall. We go down to Northcraft, and now we're closer to civilization or whatever, I guess. Can I go to my... So this map has been super helpful to us, but you might remember a couple letters ago, I needed to know where I was. And so I took the time to add roads so I could just get my bearings. And maybe I'm the only person that feels like they need to do that. But I did feel like I need to do that. And so if we're going down to the Northcraft, which we are for a few more photos, it's north of US Highway 12. So Centralia is right in here, for instance, Olympia. So these are kind of the foothills. As Lindsay Malone pointed out on social media, I think most of this stuff is locked up in logging, tree farms and that sort of thing. So maybe there aren't a lot of public places to do some hiking, let's say in the Northcraft. But we'll keep hopping around in light blue. Jamie McDonald's in the live chat. Very nice. Thank you, Jamie. So let's go to the Northcraft. And Olympia Gary took us there last time. Thanks for that, Olympia Gary. This time we have another viewer, Jeff in Tacoma. Jeff, thank you for watching. And Jeff has some photos from a quarry within the Northcraft, and he indicates these are lava flows in the quarry. Jeff in Tacoma is Jeff Tepper. Thank you for sending the photographs. So here's some UPS students with Jeff. More Northcraft. This says 45.8. Lava flows stacked one on top of another, or maybe this is just one lava flow. I'm not sure. The point is, I think we know what the spidergrams look like. I think we know what the barium to niobium ratios are based on what we've done so far today. And these are the earliest days. You remember now, as we look at these photos, these could be basalts, andesites, dacites, rhyolites. Remember the whole BADR suite. And again, you know my hang-up, it's an obsession at this point. Do we have towering stratovolcanoes or not? And even if we have towering... In the early days of the Cascades, even if we have towering stratovolcanoes, Are they in the water? Is it a coastal plain and there's a few stratovolcanoes, even if we have them? It's not the high Cascades with stratovolcanoes perched on top of these rugged ridges that we already have, I don't think. At this point, I need to get off of that, but it would be nice to have a visual. I mean, ideally, by the end of the alphabet, we have some sort of artistic portrayal for each decade. That would be fun. Is that silly to even hope for? Like, here's a hand-drawn sketch of the look of the Cascades in the light blue time. And it's mostly sea level, and there's some different kinds of volcanoes erupting kind of in the water. And then here's for green, the 30s. And it's even more submarine. And there's a few things kind of shooting out of the water, but otherwise it's mostly underwater, according to the Ohanapakash, I guess. And then now I'm ahead of myself. Now the 20s, we've got these massive calderas, and we're finally above sea level. I'm making all this up, by the way. We're finally out of the water, and we have massive calderas, massive plutons. It's the roaring 20s, and we finally have some sort of landmass that's emerging from sea level, never to go back. And then in the teens, the brown-yellow time, we've got lahars and still kind of low because the Columbia River basalts are crossing the crest of the Cascades. And then it's in purple time, and maybe it's younger than 3 million years that we finally uplift dramatically and get a mountain range for the first time, and the rain shadow effect started. Okay, Daddy's dreaming now. Come on, man. What are you doing? Granite Falls, a case study for us. It made the chalkboard, everybody. Granite Falls, way up here. There's a Granite Falls Pluton. There's a town of Granite Falls. Photos from Jeff in Tacoma, Jeff Tepper. This is Joe Dragovich, who keeps being brought up by our guests. I've tried. I cannot get Joe on Zoom for whatever reason. It's just not working. Granite Falls Pluton, Jeff's date 45.3. Mafic enclaves. So the photos are fine, but let's actually go out to this place with Jeff Tepper. Shall we? Beautiful. Okay.
All right, so there's a nice face.
Walk us through what you see here, please.
Okay, so one of the themes we might carry on through the day today is that there are several plutons in this general area that are not greatly different in age, but have a very different story to tell.
Okay.
And so the Granite Falls stock here is an early Cascades pluton, which means it's related to subduction. And we would like to have a way of identifying this as being a subduction-related igneous body as opposed to some other sort of crustal melting story. And so what we can see in this outcrop are two things that tell us this is a subduction-related rock.
Okay.
So one is that there's a fairly abundant dark minerals in here, and they're black, and that's hornblende. And so hornblende, we've talked about before, is a mineral that has water in it, and therefore is particularly associated with subduction zones where there's more water than other tectonic settings.
Thank you.
And then the other feature here are these dark inclusions.
Yeah.
And those are also very typical of subduction-related igneous rocks.
They are.
Yep. And those are a magma injection story. So those are often called mafic enclaves. And the way they form is that you have a body of granitic magma.
Yeah.
And then injected into it is a pulse of basalt. And the basalt being much higher temperature is more fluid. And so they don't mix together very well. There's a big viscosity contrast. So the mafic magma tends to break into blobs and never really homogenizes. And then it quenches and solidifies and remains in a discrete feature. So these are an indication of multiple inputs of basalt into some magma body that was sitting somewhere in the crust. We don't know exactly what depth this was, but they're very typical of subduction-related activity. For example, in the Idaho batholith, you would not find these because we don't think that the Idaho batholith was generated by input of mafic magma from below.
Yeah.
That was a crustal melting story related to crustal thickening and radiogenic heat produced by radioactive decay.
Let's keep going.
Well, that's on me. Oh, God.
All right, so often, and I can't make for sure in this case, but often crystals from the host can be found inside here. So they've been exchanging.
No kidding.
So I can't say for sure that these are that, but in some cases where there are distinctive crystals in the host, which is what we call the granite the host, you find them in here. Sometimes around the edge, and this isn't one of those times, but when a magma cools fast, it tends to be finer grained.
Okay.
And so sometimes the outer edge of the enclave, or the xenolith, is finer grained because this was hotter, this was cooler. When you mix the two together, this cools very fast and the edge becomes finer grained.
This is brand new to me. I've been in.
One more.
Solidified.
Huh. Okay, so far we have subduction generated magma because of hornblends and because of mafic enclaves.
Right. And so this being one of the older plutons that has the traits of a subduction zone is part of our evidence for when the Cascade Arc turned on.
Thank you. So Tatoosh Pluton, supposedly.
There'll be enclaves.
Spirit Lake Pluton.
Spirit Lake will have
one
enclaves. I would be willing to bet.
Snoqualmie batholith.
Tons of them. Yep. They're everywhere. Once you see them, you can't miss them. It's kind of cool over here if you want to some point work our way over here.
Few things here. How you feeling? Looks like we got more than 1,000 live viewers. That's kind of fun. Yeah, man. So we'll keep that going. People are interested in this. The format is using these photos, but also video clips. So I'm particularly pleased right now at the moment because when I started going out with guys like Jeff Tepper and starting to think about this coming winter, the Cascade series, I was looking for ideas that I could explore during the alphabet, check. And I was filming as I was learning. I mean, it's just me and this little iPhone and this little handheld gizmo that I have and a couple of mics, and I've improved the mic setup thanks to Nat the Wonder Boy since then. So that audio's a little rough now to my ear. But my point is, I was hoping when I was filming some of those things and was listening for segments that I could use in the wintertime. And that's exactly what we're doing right now. And I can barely hear it because of the audio setup here, but I think it works because we're setting up this context with interesting questions, hopefully to you, not only the geochem spidergrams, but now this kind of tangible stuff that anybody can do when they're out looking. And I've heard from many of you since that video was shown late summer. I've heard from a bunch of you like, yeah, I see mafic enclaves now everywhere I'm hiking or driving if I can't hike anymore or whatever. And so we'll keep our eye on hornblends throughout the rest of the alphabet. We'll keep our eye out for mafic enclaves. Tepper says we're not going to run out. If it's a magma from a subduction zone in the Cascades, we're going to always find those mafic enclaves. Now, he's probably bristling I said the word always, but we're introducing characters almost like the green M&M. These are mafic enclave characters and little black needle hornblende characters. We're just going to keep carrying them through and following them and see if we have any changes. This is fun for me, and I hope for you as well. Let's keep the road trip going. Back to a few photos and custom maps. It's not just photos from the viewers. So we return to the Seattle area in the Issaquah Alps in the Tukwila Formation. There's just one number here, but you know that Aaron Donaghy is hoping to come back to Washington in part to study the Puget Group, the Tukwila Formation, and many of those other units. And so she will find some new dates that will dramatically improve the correlations and the details in these units like the Tukwila. Very much looking forward to that and assume that she will be get funded and do that. But for what did the viewers come through more with the Tukwila Formation? Terrible grammar. Tom from Maple Valley sent me a few links yesterday and found this map I didn't know existed. This is Daniel Coe, Washington Geological Survey. There's nobody than Dan Coe. I visited with Dan on Monday when Jordan Carey and I went over to Olympia to visit with everybody over there. So here's a pleasing map of the Issaquah Alps where much of the Tukwila Formation is on display. Back to the maps we saw last time from Tom in Maple Valley. He was showing us some photos. I got a few more photos from Tom and Lindsay. But all these light blue areas, this is Interstate 90. I have to admit, I've never hiked in the Issaquah Alps, and I'm sorry to say it this way, but as an East Side guy who's usually hiking and there's nobody around, my only observations of the Issaquah Alps is I'm on the freeway and I see all these cars lined up at the trailhead, and I just go, those poor bastards are hiking in the rain. And you got to walk 15 minutes just to get to the trail from all these cars parked. There's too many people that live over here. Sorry, I had to share that for some reason. All right, so Issaquah Alps. Thanks to Tom, I'm seeing photos of areas in the Issaquah Alps that I didn't know existed. There's something called the Grand Canyon of 15 Mile Creek that is exposed bedrock. I'm not really sure if this is sedimentary or volcanic right here, or even plutonic, I guess, of the Renton Formation, also part of the Puget Group. Thank you, Tom. So maybe I should park with everybody else and walk in there. Looks fun. Excellent photograph from backcountry Lindsay, who lives in Seattle. Maybe Lindsay still lives on Queen Anne Hill. Her address is, just kidding. And Lindsay says, here's a photo from the Issaquah Alps using the color scheme properly, looking off to the west and seeing Blue Mountain. That's orange time. The Blue Mountain unit is maybe more light blue, but you're right. The whole Crescent story, the whole Silesia story is in that 52 to 48. And Lake Sammamish, Lake Washington, downtown Seattle. Thank you, Lindsay. And even South Seattle with the McDonald's wrappers are there. So that's Tukwila. Thank you so much. I think I screwed up here. I meant this circle to be up here at Mount Persis. If we go to Mount Persis and Young's Creek, as I understand it, Mount Persis are mostly lavas, and there are some plutons nearby that are assumed to be chemically the feeders for the Mount Persis volcanics, including Young's Creek Complex. So there's a whole range, as we're about to hear with Jamie McDonald, there's a whole range of ages and potential tectonic stories coming from the Mount Persis volcanics. Again, Jeff's roadmap just gives us one date, but he knows it's not just one date. He's just trying to be elegant and simple, which I appreciate. Here's Jamie talking about the Hornet's Nest, otherwise known as the Mount Persis area.
And I will sort of jump in the gun here, but
Go for it.
my interpretation of some of the weird geochemistry in the Mount Persis was a ridge subduction. This is before the break-off models. This is before you were allowed to be a Cascade Volcanic Arc and be that old, right? Into the 40s. That was a no-no,
Yeah.
right? And so in 2013, I gave this conference presentation at the I think it was a national meeting as a poster, and I have the poster if we want to we want to look at it. And we reviewed all the ages, we reviewed the geochemistry, we reviewed the geology, and um, and I suggested that it was a ridge subduction that then transitioned into arc geochemistry,
Hmm.
and everyone's reaction was, what arc? The Cascade Arc didn't exist yet. And I felt kind of like, oh, geez, because I was beginning to go into the Eocene because, and really the Cenozoic, because I'm a Mesozoic guy, because of the work with Joe Dragovich and the wonderful collaboration he had established. So I thought, oh, maybe I've gotten too in too deep too quickly. Um, I feel vindicated now that Jeff has written this
Yeah,
paper
yeah, right.
because the chemistry of the rocks um, can only have formed in a continental arc and in a weird setting. Um, they have all these fancy names, but the rock that was really weird was something called an adakite. What in the world is an adakite? An adakite is it's originally named after Adak Island and the Aleutians. And the K's are two very famous igneous petrologists, a husband and wife team that worked at Cornell for a long time. The K's originally defined the Adakites as the melting of the downgoing plate in a subduction zone. It is very difficult to melt the subducting oceanic crust because it's hard to get that hot below a subduction zone. As you and I know, the downgoing plate doesn't melt, it loses its volatiles like water and carbon and sulfur and a bunch of other stuff. And those volatiles act as a flux and they lower the mantle's melting temperature of the asthenosphere that sits on top of the subducting plate.
Hmm.
And then that melted mantle only partially melts, and everybody knows that partially melted mantle makes mafic magma, right? And so
Yep.
then the mafic magma rises to the surface and edifices itself as a volcano. It's very difficult to subduct.
Okay, thank you, Jamie, for that. If Jamie might still be with us live. We're into the Adakite portion of the program. Let me revisit a few of the things that Jamie was mentioning, and we're going to also use this at Tomonowous Rock in just a bit. So as I'm currently understanding it, when you get to an Adakite signature within the geochemistry of a volcanic rock, something's up. And there's a general piece of evidence that, well, I'll just say it that way, something's up. So when I was taking notes with my visit with Jeff Tepper coming in just a bit, Jeff made the point that the Mount Persis volcanics, which Jamie McDonald was just talking about, have some adakitic affinities. And the Northcraft, where we just were, down by south of Chehalis, the Northcraft has some adakitic affinities. And as I was taking notes with Jeff, which you're about to see, one way to interpret the adakite is that we're melting the subducting slab itself. We're not doing the mantle wedge thing. That's not what this is. You know that when we were talking about an immature wedge that was getting more and more mature as we were pumping more and more barium into this thing, that's not melting the actual slab. It's getting water out of the downgoing slab, water and other elements going into the wedge. You're only getting an adakite if you're somehow melting the part of the slab. And so when we go to Tomonowous Rock, there's going to be adakite, where we're melting the subducting slab. It's an unusually hot situation, and quite often Jeff Tepper is interpreting when he finds some adakites that it's the leading edge. It's the leading edge of this broken thing, because remember, the other part of this Farallon plate has already broken off, and that's the thing that's going to sink down beneath Idaho. And so when Jamie is noticing that there's adakites in Mount Persis, as well as Jeff Tepper, Jamie went the step further and thought there was a slab window, that there was truly a subducting spreading ridge. And I guess Mike Eddy is saying the same thing, although maybe the timing is wrong. Maybe the green M&M is on its way back north to Canada. But I don't think Jeff Tepper just continues to visualize a downgoing Farallon plate. And Jeff Tepper, I'm not sure, does want to lean heavily into a slab window at Mount Persis. So we might find another little difference of opinion between two experts, which is totally healthy, by the way. Let's keep going. I have to finish blue today. I can't go crazy here. I got to keep the pace going. So if we go to Mount Persis, and again, for me, I usually don't know where I am on these maps until I put it something that I can recognize from my own drives. So, Index is nearby where there's a Nick on the Rocks episode. Persis is towering above this. Monroe is at US 2, and Everett is off here to the west. And so thank you, Tom, for this map. There's more of the blue that got cut off, but I just wanted to show how much of the Persis lavas and that whole family of lavas is nearby. Backcountry Lindsay with another photograph. Now, Lindsay knows that Fuller Mountain here is tied to the Persis story and may be interpreted as a little intrusive center, maybe a plug of stuff that fed the more regionally extensive Persis. And Gary Paul said he tried looking for a few photos that he took of Persis long ago. He just can't find a good Persis photo. So we've got other images, but I confess I still don't really know what Persis looks like. And I'm enough of a rookie over in that neighborhood to still not really know where I am half the time. Thank you, Lindsay, for another photograph. Jamie McDonald has some slides for us. There's an age range here for the Youngs Creek Pluton material, 43 to 39. So we're just inching into the green time. And Dragovich and others, including Jamie, suggest the Youngs Creek was one of a number of intrusive centers for the volcanic rocks of Mount Persis. Fuller Mountain, Drunken Charlie. Youngs Creek, nearby, one of the magmatic sources of the volcanic rocks of Mount Persis. Thank you, Jamie. Jamie's heading off to lunch. Thank you for joining us live. Yeah, it's lunchtime in Florida. If we go across I-5 and head out to Tamanous Rock, that's our other key study spot. It's in the light blue. It's got adachite. And I was out in the field with Jeff Tepper in July. We're heading out towards the little town of Chimacum. Chimacum near Port Townsend and Tamanous Rock. Culturally a very important place for indigenous communities, but also an important place for our story about these earliest Cascade volcanoes. Ken Clark artwork, Tamanous Rock here. If you happen to know Chimacum and the crossroads there will be some of these panels that will be installed. Maybe they're already up, Jeff, I don't know. Gary Paul's been there. Towering photo of this chimney of Tamanous Rock. It's early Cascades magma, but what is it? Is it a lava flow? Is it a pluton? Is it an adachite? Is it just like Mount Persis? Is it different? Let's talk to the expert.
So we might be able to find some in here. I mean, one thing we can see right offhand is that this cliff is made up of angular chunks of rock, which are all cemented together now to make a very resistant surface. But this was never a lava flow. This was a product of a much more explosive eruption where the material was broken into blocks, and then those blocks went rampaging down a valley, ultimately came to rest, and then solidified. So this was an ash flow.
Ash flow.
Not a lava flow.
Was it clear, is it clear where the vent was, that where this flow was coming from?
There's
He looks over his shoulder like it's a secret.
can't tell anybody but you and me. Well, there's no vestige of the actual vent left. So this was happening 40 million years ago, and since then it's been glaciated, and so a lot of the original topography is long since erased.
Right.
But we have several clues that we can use to infer that we are close to where that vent was. So one is the size of these blocks.
Size of the block.
So some of these blocks, like this one, I mean, that's
Yeah.
approaching a meter in diameter. So
Sure.
the bigger the block, the less distance it would have traveled from the vent. And the other clue we have is if you look at a geologic map, there's the area that is covered by this rock is greatest here and much less moving away from here. So the eruptive center was probably here where most of the rock is, and then fingers of ash flow would have radiated in multiple directions down valleys, but they're much less voluminous than what's right here. We're next to a state park, Anderson Lake State Park,
Okay.
and we are standing at the face of part of Chimacum Ridge.
Okay.
And so Chimacum Ridge and the area around Anderson Lake have the most exposure of this rock.
So these blocks are all the same composition?
As far as I can tell,
And what kind of rocks what kind of volcanic rocks are we looking at here?
it's somewhere between an andesite and a dacite. So
Okay.
it's a fairly silica-rich rock, which is part of the reason it was explosive. Initially erupted and forming the flanks of the volcano, and then when it exploded, the flanks of the volcano were blown into pieces, and those pieces then were incorporated into this violent ash flow. So this rock, these chunks of rock solidified as part of the volcano first, and then were later remobilized into this ash flow.
So what kind of volcano are we visualizing? Is it a stratovolcano like St. Helens appropriate, or is this possible we're
This
into
is
a
probably a lot smaller.
smaller?
So this type of eruption is associated with a dome volcano, and that's what's growing inside the crater at Mount St. Helens today. So domes tend to be, as the name implies, they're steep-sided and probably typically not more than a few thousand feet tall, whereas a big stratovolcano could be 12 or 14,000 feet tall. So this is a much less aerial extensive kind of volcano, and not as tall and steeper, but also more explosive most of the time.
Okay, well, do you have a visual? Jeff's using his words, giving us a visual, but he has the benefit of working with Ken Clark, his former colleague at the University of Puget Sound, and Ken has artistic abilities in addition to geology abilities. So this is the visual for that former volcano 43 million years ago, which is today at Chimacum on the Olympic Peninsula, but it's not a Silesia story, it's an early days of the Cascade story. And here are these ash flow tufts barreling down these valleys. Well, okay, new thought right now. If we have valleys, we have mountains. If we have mountains, then it's not this at sea level thing in this coastal plain deal. So I guess at some point you might all just get me off of this. But I keep coming back to wanting a mental snapshot almost by decade, but even more than that. Like early 40s, it looks like this. Late 40s, it looks like this. We probably won't get there, but that's where I naturally want to go. Put a volcano like this in context somehow. Are there 32 more of these things, in Washington at the time? And we just have one of them to look at? One fragment of one of the ash flow tufts to look at? And we only have that because this former valley was an open valley, and then here comes this ash flow barreling down this valley, and then it's now inverted topography where the valley is now the ridge, and that's the chimney that we're looking at in the middle of the trees. I mean, gosh, there's this about geology. we just have a few fragments, a few tiny fragments of major amounts of the story to work with. We're trying to tell the whole story, but we just have little scraps here and there to try to put a story together. It's fun. It's detective work. You've all heard that. But in this particular case, now that we've started the subduction zone, I keep wanting to have a mental picture, even a gross, broad picture of what the Cascades look like in Washington by decade, by color. Never really had that moment, never had that thought till this moment. And I probably won't get off of it for the rest of the alphabet. So this is yet another thing to annoy you, because I'll keep bringing it up. All right, good. We're still at Tomanowos Rock, and we got school kids screwing around in the background, and Jeff is concentrating like a boss. And now he's going to introduce this concept of hornblende being a helpful subduction zone magma feature.
Here we go.
Okay.
Is that too small to... So that little brown rectangle is,
Sure.
is an amphibole crystal, and it's brown because it's rusted a bit, but it was originally a jet black color.
Okay.
And the importance of that is that that's a mineral
really
that
steep, you guys.
I'm not forcing.
that's a mineral that contains water and actually in the mineral, and so it can only form in a magma that has water. And subduction zones tend to have a lot of water. So this is kind of the fingerprint of a rock that's associated with a subduction zone, whereas the crescent lavas that are not associated with subduction zones, they never have amphibole.
Okay, well this is a big moment. So we're on the Olympic Peninsula. There's a bunch of lavas, many of them tied to the crescent and the Silesia story where we were erupting under the ocean water. And you weren't the first maybe to say this cannot, or maybe you were, this can't be a Pacific Ocean Basin eruption. Because of the hornblendes, we have water. This has to be subduction generated lava.
So it's a very tiny piece of evidence, but it has this
Really cool.
sort of plate tectonic scale story.
That
to it.
is so cool.
One more from Jeff. When I was struggling mightily, it took me, that's one of the themes this morning, I guess, the repetition to finally grab hold of something mentally that works for me. I don't know about you, but for me, I was not getting that Farallon plate sliding north at all. And this is about the fourth time when we filmed this in July that I heard this from Jeff. I still couldn't see it. But this is a moment where he found the right words that was starting to work for me a little bit. And now I think I totally see it because of our work with the green M&M discussion.
So as we hike, Jeff, I can maybe hear some of the viewers right now like, okay, I don't think I get it. Why is Chimacum the birthplace of the Cascades if it's so far away from the Cascades? And the panels are going to help with that,
Right.
but like maybe you can try it verbally just with a few
So
sentences.
I guess I'm equating the birthplace or the birth of the Cascades with the renewal of subduction. And Chimacum marks a location where we are confident that there was a subducting plate beneath us. And beyond that, it seems like it was the leading edge of that plate as it was moving northward into place.
I got it.
Okay, now the other thing that is...
No, but I got it. Let me just enjoy this moment. I can see it really for the first time.
All right, I'm having a teaching moment too.
Okay.
All right, very good. So the Adakite thing continues to come up, but it's the Tomanowos Rock area where that became new material that I wanted to try to learn a little bit more. So this is back to yesterday. And is it? Yeah, it's yesterday. Sorry, this is not July of 2024. This is literally yesterday, January of 2025. Jeff, add a little bit of a bow on our Adakite creation.
Dates, they're all uranium, lead, zircon ages. So I think the ages themselves are good, but there's no reason that they all have to be the same. There could be several million years of activity in the vicinity.
Is there a reason you did not put Tamanous on this list of older dated Cascade units?
Not really. It's
Okay.
it's different. It's an Adakite, so it's not a normal arc rock.
Yeah.
So I guess what this Ken Clark drawing that you're looking at now was intended to convey is that why is there an Adakite at Tamanous Rock? And the interpretation we have is so that an Adakite is the result of melting of the subducting plate. And traditionally, and I might come back to this as well, it's been assumed that the plate only melts when conditions are unusually hot. And so unusually hot conditions can arise in more than one way, but being in a place where you're at the edge of a plate and hot mantle is right next to it, that's a very thermally favorable place to have Adakite formation.
Yes.
So our interpretation of the Adakite at Chimicum or Tamanous Rock was that it was the leading edge of the plate that was moving north, and as that plate moved into hot mantle, it was melting, and then Tamanous Rock is just a sample of that melted material.
Do you have any other? Okay, we finish our road trip, and we are approaching finishing the episode down here in the south, the Gobel Volcanics. And so if we go back to Docky one more time, now we're down in the neighborhood of the Spirit Lake Pluton. Here's Mount St. Helens. Spirit Lake Pluton is just to the north. I'm going to be curious how much when we finally get to the Spirit Lake Pluton, something like the Gobel Volcanics might crop up, and so on. But this is, Goat Rocks is here. Spirit Lake Pluton is here. Haven't forgot about those projects. That's why I'm whipping myself to make sure that I'm pushing ahead with the alphabet. We have to get to those two projects. Those two projects are the reason that we're doing this alphabet with the Cascades. We have to get there. But let's finish blue in the last remaining moments that we have together this morning. To the Gobel. And Jeff Tepper again, sending photos from some of the dipping lava flows exposed within the Gobel Volcanics, 41.1 million years old. So we're now approaching the end of the early days, quote unquote, of the Cascade Volcanic Arc, as we're defining it. We're about ready to turn to green. Is this one flow? Are these a series of flows? Do they have mafic enclaves? Maybe mafic enclaves are more typical of plutons than they are lavas. Are these adakitic as well? Tough with charcoal. Jeff, I don't know what to make of that. Like, my mind goes to coal, and my mind goes back to eruptions within some sort of sedimentary boggy area, but maybe charcoal means something else. Maybe it's some sort of violent ash flow that's going into a forest or something. And the tuff, beautiful. See you later, Gary. And the vent breccia, all these details preserved older than 40 million years ago. So we can get that kind of preservation of volcanic centers from light blue. And you remember one of my questions last time, why isn't the light blue buried underneath all the other colors of the rainbow? And I guess it's a clockwise rotation story, but there were a few problems now that I saw some of your comments after that, explaining the blue being naked and all the rest of the colors stacked up on top of each other Maybe it's more than just a rotation story. Vent deposits. Yeah, if I saw those without any context, I would not guess that they were more than 40 million years old. I'm just realizing, I'm just having that thought right now. I think this was Pleistocene. I think this is something that happened less than 1 million years ago. 41 million years ago, and there's a bunch of vent deposits just hanging out? Nothing happened here for the last 41 million years? Really? Wow. Thank you, Jeff. So that's the end of our road trip. We have a couple final thoughts from Jamie McDonald and Jeff Tepper, and then we set up transition to green. Jamie.
With relationship to the subducting plate that lies below them, right? There's this concept in tectonics called an arc trench gap, right? So if you go from the 40s into the Oligocene, right? So if you go from places like Granite Falls Stock and the Hanson Lake Rhyolite and the Youngs Creek Intrusive Complex and the Drunken Charlie Lake and the Mount Persis, the Cascades are starting there, but then they migrate inland to where you have the Index and the Grotto and the Snoqualmie batholiths.
That's what I was about to draw, man. This is perfect.
Man,
we're in sync.
Look at this.
This is good.
It tells me that the downgoing plate is shallowing, and it's forcing the arc inland, right? Because the volcanic arcs have to be 100 to 150 kilometers above the downgoing plate, because that's the sweet spot where the downgoing plate loses its water and other volatiles. It hydrates the asthenosphere that sits above it, partially melts the mantle, and then the mantle is hotter than the rock that surrounds it and less dense than the rock that surrounds it. So it rises up towards the surface of the earth, edifices itself as a volcano, right? It has to be 100 to 150 kilometers. And as this is the downgoing plate, this is the overriding plate. As you change that dip of that downgoing plate, the arc's going to move around. And so during the 40s, there you have all these nice blue rocks in the 40s. I apologize, mine were orange. You have all these nice blue rocks into the 40s. But then when you get to the Index and the Grotto, everything shifts to the east. So that tells you something's going on. Subduction, the slab might be shallowing, or for some reason the volcanic products are shifting to the east. Then the modern arc is out to the west, right? That's what's going on with this slab, right? Is this slab doing?
So, I think that's an open question. Rotation versus playing with the angle of the subducting oceanic plate. Do we have to pick one or the other? Is it some combination? It's less satisfying to say it's a combination, but maybe we can keep thinking about that as we go. One final video clip, and then we wrap this one up. The Cascades as a whole, how unique are they? Jeff Tepper.
They lack the arc signature. So the mantle is heterogeneous. That's the takeaway.
And I think the takeaway I'm hearing from you pretty much all during this session is you're kind of open to some major changes with geochemistry up and down the arc, at least in this time frame, but maybe throughout the 46 million year time frame of the history of the Cascade Volcanic Arc, and still have it be a relatively simple tectonic story, a convergent plate boundary, oceanic plate diving beneath a continent. And if we get to a point in the alphabet where we're like, my God, we've got all this crazy stuff going on. We've got these niobiums are going up and down. You're like, it's okay. It's still just an arc.
It's the norm. It's the norm.
It's the norm.
I think one thing that is exceptional about the Cascades is that the plate story has been relatively constant for 40 million years. We can discuss which plate was subducting, but it has been a continuous process,
right,
for 40 plus million years.
Yeah.
And so that's a it gives us an opportunity in a relatively recent arc, not some ancient Andean thing, but something that's been is recent
Yeah.
with a relatively simple geometry. And we can ask the question then, how is it changing if that parameter, that fundamental parameter, is kept constant? And there are all kinds of other levels of, what it's just to say, well, it's, a subducting plate. Well, the plate is segmented, so it can have tears in it.
Yeah.
And the crust is not uniform. The
Yeah.
crust is different in Oregon than it is under Washington. This is the Columbia embayment story. So all of those things are going to, and there's a change in the stress regime because you change the angle of the arc relative to the angle of the plate. All of those things influence the magma generation process. And so what to me is cool about the Cascades is that at least in Washington, we have rocks that span that whole 46 million years. We don't have them so much farther south because the erosion level is not as deep or stuff's been stripped off. But in Washington, we have a 45 million year unique opportunity. I would say there's no other arc I know of in the world that gives us that view. So that's going to be my hobby for the next 10 years.
Thank you for all your help, Jeff Tepper. We are done with the Tepper trilogy. If we look, we're done with the breakoff belts. We've started the volcanic arc magmas. We start 46 million years ago, but all through the 30s, all through the 20s, all through the teens, all through the aughts, this will continue. And we have some narratives now established from the early days of the magmas in the early Cascades. So we're done. We're officially done with the Tepper trilogy. We're ready to move on to the Ohanapikosh. We're done with the Tepper trilogy, the paper that's coming on breakoff belt magmas, the paper that you have for the Chalice rollback magmas, the paper that came out just a few months ago on the Cascade initiation papers. And yes, this whole concept is firmly established now, and it will just be unclear, and we will explore together stories that we run into together. Like this, a sneak peek to the next weekend, the next 2 episodes. We're heading to Green. We're heading to the Ohanapikosh. We're heading to Mount Rainier National Park. And if you liked those videos that I filmed in Mount Rainier National Park, I did too. And the Ohanapikosh was the scene stealer for me. I got deeper and deeper into thinking about the Ohanapikosh last August and September, and that was just as I was reading field guides, as I was filming a little bit, and I haven't done much more thinking than that. So we will do it together in the next couple of episodes. And as we keep track of the stories that you and I have been putting together, we're done with light blue again. I said this at the beginning. I want to say it again right now. This is all I have in mind for places to visit and study for all of the decade of the 30s. All of the decade of the 30s. And I'm asking you, viewer, if you want to email me with some additional potential leads for us to explore during Green, during all that decade of the 30s. That's 10 million years worth of time, somehow tied to the Cascades. I can't promise I'll reply to every email, but I will thank you in advance for any of your creative ideas, and I'll pick and choose what I like in addition to what I know that I'll do with Ohanapikosh and Index. We have a sexy video from Mount Index, which apparently Cascade PBS just submitted that Mount Index episode for this summer's Emmys awards. So we'll see if we get nominated, but PBS has put their money behind submitting that Mount Index episode. And to see Gary Paul all dressed up would be worth it just for that. So that's Green, and then you know where we're headed there as well. A toast to you for joining us today. Here's to you for joining us. We still have more than 1,000 live viewers. Do you have some questions? Let's do a few questions. This one's running long, and I thought that it would, but we're trying to wrap up Blue, and we have wrapped up Blue. So let's spend a few extra minutes with some live Q&A. Uppercase, please, for questions tied to today's show. I think we lost Gary Paul, we lost Jamie McDonald, but we still have Jeff Tepper in the house, who I'm sure has been answering a bunch of questions all along. Saber, is it predicted that the barium-niobium ratio will continue to increase, or will the barium saturate and level off? I think with that plot, Saber, Jeff has shown us graphically that we will continue to increase. We don't have to guess. I think we saw the whole story. And maybe Saber's asking, in the last 2 million years, have we saturated and will the level go off? Jeff Tepper, I don't know if we have any modern lavas to compare with the barium-niobium ratios. North Scotty Nerd, any pillow basalts present to confirm that the early arc was erupting underwater? That's a great tip. Thank you for the question. Keep an eye on for any indications of sea level, whether it's from the sediments or looking for pillow basalts or looking for any kind of explosive, I don't know, so now we have to ask a volcanologist, I know the answer to that question. We will look for indications of former elevation. That's the best way to say it. Pat Miller, how far down into the crust mantle does the rotation extend? Great question. I don't know if anybody's got an answer for that. Maybe a simple answer is at the brittle ductile transition, which is maybe 15 kilometers down. Maybe things are so gooey, they're solid, but they deform ductily. Maybe that's, I don't know. I wonder if anybody does. Thank you, Pat. Kelly, would Silesia solidifying its parking place over time explain the eastward migration of the arc? Solidifying its parking place. Maybe we will go in that direction, Kelly. If we keep following the north, let's say the crest of the Cascades is just that, and it's a north-south crest. And Jamie was talking about that crest jumping east for a while and now more recently jumping back west. What factors go into shifting the crest position? Chance, clockwise rotation, playing with the angle of the subducting slab, tears in the slab, or E, all of the above. Baba Yoshi, did Silesia accretion create a temporary uplift that is present here in the late 40s, but once the plate slips out from underneath it, it switches back to decompression and we drop back beneath sea level? Interesting thought. I think I'm just curious about trying to lock into elevation up. I think you're going further than I want to go. I think I just want to know, are we out of the water or in the water? That's maybe the new way that I'll try to deal with this. Are we underwater or are we out of the water? You're like, you're always out of the water. It's the Cascades. Well, I think that's what we're going to find in the Ohanapakash. We're mostly underwater during at least the late 30s into the 20s. I think we're underwater. That's why I was so fascinated by that Ohanapakash. And I picked green because the frickin' rocks are green. Tune in next time for green rocks, but not serpentinite. Mr. Tony, does the angle of subduction impact the levels of barium over the year? I don't think so, but I'm not sure. Kyle Roth, location of the Cascades, would they also be the same distance from the ocean trench? Thus we can forget clockwise rotation. I think Jamie was talking about that, Kyle. And I love set rules like that. The trench is here, and so we have to have the arc here. But I think we are noticing I don't want to say migration again, the shifting of the crest position. And why are parts of the crest today offset from other parts of the crest? We get into all that. A few more. Thankfully, we have Jeff. Jim wants to talk about the owl. Gene wants to talk about Hansen Lake rhyolite skipped over. What's the story there? Thank you, Gene. They have this right. The Hansen Lake was on our road trip itinerary, and I skipped over it. Why? Full disclosure, I was with Jeff Tepper at Granite Falls, and then we went over to the Hansen Creek rhyolite and filmed there, but Jeff's mic ran out of battery. So I scrapped some good stuff at the Hansen Lake rhyolite. And the Hansen Lake rhyolite is the equivalent of the Granite Falls Pluton. So I guess the answer is I just didn't have anybody send photos of the Hansen Creek rhyolite or the Hansen Lake rhyolite. Plus, I don't have any salvageable video, even though Jeff took a while to figure out where that outcrop was. We finally got there after a little bit of lunch, and microphone didn't work. Glenn, can the chemistry signature of the mafic enclaves into the host Pluton help track changes in the subduction angle? I'll leave that one to Jeff. I like you guys are fascinated by the subduction plate angle. I just don't know how you would use geochemistry to do that. How do you reconstruct the angle of a slab except looking at where the magmas are coming up? That's a rather basic question. But sometimes the basic ones are the best ones. Kent, might the barium ratio in the wedge impact future breakoffs? Impact future breakoffs? Not sure I get why you're asking it that way. I don't think we're going to get a future breakoff until we accrete something major again. There was a reason that we had a breakoff. Pacific Basin reorganization combined with a massive plateau slamming into our shore, or us slamming into it. So it doesn't seem like we're headed for a new breakoff anytime soon. 3 more and we're done. Scrolling way back. AF Winter, Slow Life. Is there a chemical signature if the volcanics erupted into saltwater versus freshwater? Good question. I don't know. Probably not, but don't know. John, does that ash flow tuff formation imply a dry environment? Does it form pillows in contact with the water? Maybe those explosive ash flow tuffs are so violent that it's anything that the ash flow is barreling down is not preservable. So if there's plants in the way, they're destroyed. If there's water in the way, it all turns to steam. I think that's why sedimentary basins, quiet sedimentary basins, are valued in this case. They do have the precision and the delicate nature where they can record details of a former world that as soon as you get into some violent volcanic activity, I'm not sure you are as likely to preserve the details that we're hoping for. Last one. Another John. If the slab angle is determined by the slab temperature, can you reconstruct slab angle from the distance from the spreading ridge and then estimated rate of subduction? Thank you for the creative thought. That's another way that we go about this. When I see everybody asking about the same sort of thing, then that gives me a nudge to go in that direction. We'll see if we can tie slab angle. Once we got the arc set up, that's fine, but that's another narrative. Do we have evidence that the slab is flattening somehow or steepening somehow as the decades roll on? A toast to you. Here's to your health and the health of everyone in your community. I did the health toasts when we first started doing live streams and we were all dealing with health matters related to the coronavirus. That's gone. But it's still an appropriate toast, isn't it? Especially as we get older, we realize how delicate everything is from a health perspective. So here's to us. Our Bluebird Day has suddenly clouded over a little bit, but that's not going to stop Liz and I from getting outside. Speaking of health, we will continue to work on our end. You continue to work on your end with Health Matters. I'm not going to see you for 5 days, but when I see you again in January of 2025, we will be doing 2 episodes from the 30s, probably just 2 episodes from the 30s. But if you're really into this channel, I will see you live Thursday at noon Pacific. I will see you Friday at noon Pacific for a department-wide talk by Tim Melbourne. And I'll see you Saturday morning at 8 a.m. Pacific. Boom, 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 boom. I'll be seeing some of you 3 times live over the next few weekends. Thank you. I love you. And goodbye from Ellensburg, Washington, USA. Goodbye.